Hello everyone, welcome to this new video in our software exploitation series of videos. So in this video we'll take an application and uh, a local client application and we'll exploit it. But before I do that, I just wanted to explain maybe one important thing to keep in mind is when it comes to exploiting applications or software, we have three, I would say, especially when we are talking about applications or software running on the user side, not anything related to the kernel. Okay, so the way we can exploit them is three ways, in my opinion. Maybe I've missed one of them, but I think there are only three. So one of them is uh, by exploiting the client. So exploiting the client, okay, and this is a local exploit. So what happens in this case is you target the client application and you exploit it. For example, a user running, let's say, a multimedia application, you send them a malicious file which gets opened by that multimedia application, and you take advantage of vulnerability in it. And that's what this today's video is actually going to be about. Or let's say you send them let's say a Word document or a PDF document, and they open it with their application and you take advantage of that. Or let's say, take another example where you use, for example, let's say, what do we have? Like, yeah, I think those are all three, those, like the PDF, Word reader, maybe like an image processor or an application that opens an image, any client application that could be targeted on the local side, we'll call it like a local exploit. Okay, so you're targeting the client application this way. Now, exploiting the client could be done locally, and it also could be done remotely. What does that mean? So we could also do exploiting the client, okay, but this time it will be a remote exploit. How's that happened? So this one, let's say, like we said, multimedia application, right? We can do that. We can say like a Word processor, or let's say a PDF reader, something like that. So these are all options. Now in this case, think of it like this. Your client goes visits a malicious server. So now it's kind of a remote exploit. Okay, again, your client is now doing the visit. So you are visiting a site or a server or another location, and your application gets exploited. So this is what you will, let's say an example could be like the browser. If you browse, let's say, some evil website, like browsing to an evil website, that will happen. Or maybe connecting, because this is also going to be an example later, connecting to an evil FTP server with your FTP client. So your FTP is the client, it's a client application, that's true, but it's getting exploited by visiting that remote site or that remote server. Okay, so I would like to call it a remote exploit for a client application. I could be wrong, but I like to call them that way. And finally, exploiting the service or the process or the application, let's say, remotely. So this is completely remote. Okay, and an example of that, like exploiting let's say a running server, running FTP server, or a running let's say web server. We will see some of these examples actually. So the server is running on a remote computer or on a remote system, and you remotely are able to send some crafted data, and that data takes advantage of a vulnerability in that application, okay, and exploits that application for you. Okay, so these are the three ways of exploiting these applications. Again, I'm not talking here about any kernel level stuff. Here we are just talking about applications in general. So client could be divided into two, local and remote. Local, multimedia, Word, PDF, anything like that. Remote, it's when your client application is actually visiting an evil site or an evil service or an evil server. Okay, so anything uh, connecting to an evil service. Okay, this is when this happens. And here we are also running remote service, like service running remotely. Service, yep, good. So these are all could be considered like client exploit the different exploitation methods. We'll cover most of them, by the way. I think we are going to cover, if not all of them, actually. Okay, so these are just some notes to keep in mind. So today, our example is going to be on an application called VUPlayer. It's a multimedia application. Okay, so VUPlayer, it's a multimedia application. We are gonna so it falls within this category. Okay, so we are gonna see how we can exploit this on this Windows system, and this is going to be for demonstration purposes only. You'll see what I mean by that later when we move in through the explanation and the demonstration. So we created this, and this is, by the way, all of this is on my GitHub, so you can find that. This is version 2.49, so make sure you have this one. There could be other versions vulnerable, but this is the one I'm going with. So we'll use this code to create this bad M3U file. The M3U file is, let's say, the file which is supposed to contain a playlist, but it's actually not going to contain a playlist. It's going to contain some junk data to exploit and take advantage of a vulnerability in this application. Okay, so code is very basic. We are going to create 3,000 bytes of A's, put them in this payload called, which is called actual payload, then open this file in write mode, and then write this payload into the file, and then just close the file. So that's all we are doing. Okay, and here if we press F5, it will create the file for us. We can even write, by the way, maybe print file created, okay, successfully. Okay, so we can do that just so that we know it's done. Okay, so we now have this file, and now what we can do is go to the application and open the file and see what happens. So as you can see here, something is going on and the application crashes. Great. So it seems the application is vulnerable, and actually it is. I know it is, but again, the idea here is to explain these concepts and techniques, not like to find a 0-day in these applications. So let's get our debugger and start playing with this. So let's get the debugger, okay, and load our application. And yep, here it is. You need to navigate to the location. Just hit OK for these for now. And we have our application running. So let's run it. Start the application from within the debugger, okay, and then from within the debugger, go load that file, which is the bad playlist. Let's do that. My system needs a reboot, I think. Yeah. So open. Let's see what happens. So we can see here the application paused, and it's saying access violation when executing 4141, etc. And that's because there is no address called 41414141. Now we can see ESP was overwritten with A's. We can see EDI has some A's pointing here. We can also see ECX, excuse me, also got written with some A's here. And we can look, if we look at the stack based on ESP, this is the top, we can also see that we have a lot of A's written where on the stack. If we also go to the dump, we can see these are all A's written. So we have a lot of A's. We can see here, there's a lot of them being written where on the system, on the stack. So we managed to crash the application. We managed to take control of some registers, and we also managed to take control actually of EIP, which is very important for our exploitation. So what does that mean? It means we do have control over, let's say, a register or EIP directly. So it's a vanilla buffer overflow. That's what this is really, and that's why we have direct access to it. Now our problem here is, in the previous example or in the previous videos which we went over, we kind of knew how much bytes did we need to write in order to reach this location or to overwrite on EIP. In this case, we don't. So we are now going to introduce another tool which will help us in that. I know we maybe mentioned Mona in the last video, which is created by Peter from the Corland team. But in this video, let's take another advantage of Mona and see how we can use it. So what we need to do is we need to figure out how many bytes I need to write on top of the stack in order to overwrite my return address. What does that mean? Maybe I can like draw a basic graph and MS Paint, like a basic figure to explain the idea. So if we get this, and let's say this is our stack, okay, so let's consider this is our stack, and no, I want this, yep. And now let's consider maybe this is where just to make things easier, let's say this is where our return address is, and let's put return here, so say ret, okay. So yep, that's it. So this is our stack, and this is where our return address, which is the one that we want to overwrite with. Wait a minute, let's use another color. So yeah, we want to overwrite this with what? With those A's, right? We want to overwrite it with 0x41, 41, 41, 41. So we want to overwrite this with this value, or we did actually overwrite it with this value, but we want to find what is this location that I need to overwrite with this value, or how far is this from the top of the stack, for example, or what is the offset that I need to add to the stack in order to reach this location. So we are looking at here, how many bytes do I need to write? Okay, how many bytes do I need to write in order to overwrite the return address? Okay, so if let's say you are going to start writing from here, let's say from here you're going to start writing, okay, how many bytes do you start writing from here all the way down to overwrite these 4 bytes? How many? We don't know. Sometimes it's not easy to calculate like just manually, like the case we did in our test example. That was a basic example, so it was easy to calculate. But in this case, we need to find another way to do that. And thanks to researchers such as Peter, that's now easy to do. So if we go and like run Mona, we'll get the help about all of this, that this is all the commands that you can use, everything here. I'm going to just I want to make sure Mona is set to my desktop. Okay, I'm going to delete these just so, because these were used in a previous video or maybe for my students in class. So I'm going to do that, delete that, and now generate some data again. But before I do that, let's make sure we have our working directory or working folder set correctly. So we have users, user 1, I think mine is user 1. Let me just double check. Yep, I will user 1. And then we have desktop. Yeah, desktop. Okay, and then we have Mona. Okay, so we are, just to make sure, old value parameter is C users desktop Mona. new value parameter is the same. Yeah, so it means we already had that. I just wanted to make sure. Great. So what are we going to do now? We are going to use the mono command, okay? And we are going to use the pattern create command with it. So we want to create the command pattern. So we can either do like this, pattern, and then create, and then say 3000. We can, is that 3000? Yeah. And say 3000. We can either do that, or if you don't want to, you can just type PC. That's also similar to typing pattern create. So now if we hit enter, it's gonna create that pattern, which is now stored in the mono directory. So where is this? Yep, let's go to our desktop. Okay, now one thing about this is, let me open it. What is this? And why are we using this, and why are we making this? So this tool will create a pattern where no 4 bytes contiguously after each other will appear twice in the sequence of bytes. Again, the idea here is we are going to create a sequence of bytes depending on the size you provide. We said 3000, and there will be no 4 contiguous bytes similar in the same pattern. So it's going to be unique within that pattern. Any 4 bytes within this pattern will be unique. What does that mean? It means when I'm going to go and going to drop those bytes from here, start overwriting, those 4 bytes that get written here, those are going to tell me what is the offset from the beginning until this location. Again, we're going to throw those bytes into the stack, and now those 4 bytes which we will be seeing in EIP in the debugger, those are going to help me identify how much bytes do I need to reach this location. So what's the offset, in other words, to reach this location? Okay, that's why we are going to do that. And now again, mono, what it tells you, do not copy this because this is truncated. It's not the full pattern. The pattern is actually in the mono directory. So that's why we created it this way. Okay, I like to usually create copies of this so I can later on go back and see my sequence. What did I do first? What did I do second, etc. So I'm going to do that. And now I'm going to work on exploit 1. I'm going to copy these 3000 bytes, okay? And I'm going to replace this with the 3000 bytes, okay? So now we can close this. We don't need it anymore. And now we can run this again. Let's restart our application because it's already paused, crashed because we crashed it. So let's restart that, okay? And let's hit okay, and let's start the application. Okay, let's create this file. So hit F5, file created successfully. Now let's go back and launch the application and load the file, see what's going to happen. Okay, so we open. Great. So again, the application froze or has an access violation. It paused. You can see that here, right? And we can see that there is some value now written where in EIP, which is some 4 bytes. Now what we can, and you can see here again, these are some of the bytes that were part of our pattern. So we can see those ESP, it's got overwritten with them. We can see that on the stack. These are the bytes. They really mean nothing. So what we are going to do now here is copy this. So Control C, you can do that. And now instead of pattern create, we will use pattern offset. So pattern offset, and just give it the value, these 4 bytes. And now we can run it. And what it says that this pattern, so these bytes, are H7BH in hexadecimal. And it says these 4 bytes, which is the H7BH, are found in cyclic pattern at position 1012. What does that mean? It means that we need to write over here 10, 12 bytes. Okay, we need to write over here 10, 12 bytes in order to overwrite, reach this offset. Okay, so if we write 10, 12 bytes, the next 4 bytes are going to be our return address. Again, if we write 10, 12 bytes, okay, from the beginning, then the 4 bytes immediately after that are going to be our return address. Good. I'm not good in designing or in these drawings. I know I'm bad, but I hope this explained the idea. So good, we have that. Let's see if this is true. So let's start the application again, but this time we'll update our code. I like to, again, make things step by step and go one step at a time. It might take some time, but at least we can learn, we can understand what's going on by doing a step at a time. So let's do 2.py, okay? And now this time, let's delete this and let's multiply this by 10, 12, but let's fill this with what? Let's fill it with the A's, sorry, 41. So we have 10, 12 of A's. And then after that, let's put in EIP. Let's see if we can really put in EIP what our 4 B's. So 42, which is the B's, 4B, we'll add 4 of those, right? So now we'll have our, if we go back here, we are going to overwrite this with, let's say, let me delete this because now it's not the same. Okay. So we're going to overwrite this with A's. These will all be A's here. A, and then A, then A, like that, A, etc. Okay, and so on and so forth. And then we want to overwrite this, these 4 bytes, we want to write them with the B. Okay, these will be overwritten here. That's what we want to achieve now. Okay, good. What do we want to do next? So we got the A's, we got the B's, and now we need to just pad the rest of the payload, because the payload was, remember, the payload was 3000. That's when we managed to crash the application. So if we just send this, we are probably not going to crash the application. So we're going to do calculations a dummy way, but later on in this video series, we'll show other methods how to do this. But for now, again, I'm going to use a dummy way. So please, if you are watching this, I still know how to calculate things, maybe a couple of basic calculations. I still know that. But again, I want to use the basics here, and then we'll move to other ways later on. So for now, what I'm going to use, I'm going to do pad 1, for example, and I'm going to pad this with C. Actually, I'm going to pad it with, yeah, just C, because there's a reason I don't want to send the /xcc. I will explain that later. So we can actually just do x43. Yep, let's do that. And then we're going to pad this with the rest of what? Of the payload. So let's get our calculator and see what do we have. So we have 3000, right? Minus 10, 12, and then minus 4. So we have 1984 left of bytes left. Okay, we have 1984 bytes left. So let's do that. 1984 bytes left. Okay. And yeah, let's close this. We don't need it anymore. What we need to do now is we need to add the whole payload. So we have EIP, and then we have pad 1. And the reason I named it pad 1 is just because later on we might need other pads. So let's do that. And let's add another thing here to print. So let's say payload length equals, and then let's add the len of payload, just so that we can print that and make sure we are on the right side. So let's run this. Payload length is 6968. Why is that? Uh, how did that get? See, I told you I'm bad at math. What's going on here? Okay, so junk is this. And then we have EIP. Yeah, this should be. What's happened here again? Let's check. Am I missing something? Payload length. Oh, I know what. Okay, okay. Let me change this. This is being calculated. Let me just maybe. This is, by the way, okay, okay. This is, no, this is the reason why I found it. I forgot to add the slash here. Okay, this is taking this as 3 bytes. It was taking it as 3 bytes. Okay, my mistake. Now it should be 3000. Yep, I told you I have the basics of calculations. Good. So let's continue then. So yeah, my math is still working then. Great. Okay, so what do we do now is let's open the application, and what should happen now is we should see 4Bs in EIP. So let's make sure we have 4Bs in EIP. Otherwise, yeah, my math sucks, like people say. So yep, we have the 4Bs in EIP, like you see here, okay? And we can see the ESP was overwritten with the Cs, so it seems our payload, anything, this is also one good thing to keep in mind. So we can see that our payload, or the top of the stack, got now overwritten with the C part. So what does that mean? It means we now have control over the EIP, that's true. And now if we want our shellcode to work, we'll add it at this part of the payload. Why? Because this part is the one that, as you can see here in this case, got overwritten on the stack. So if we add our payload here, not that, by the way, not that I mean the other bytes were not on the stack, they are, but the way we want to exploit this is by jumping to ESP, and we can see ESP is pointing to our C. So if we need to write something, we need to write on in that area. So if we write in the C's area, we will achieve our exploit. So let's update this again, and this time call it number 3.py. Okay, so what are we going to do now? Let's restart the application. Yes, and start. Okay, okay, okay. Start the application. So what do we need to do now? What are we going to do now is we need a jump ESP, because we saw ESPs pointing to the top of our stack. Now again, this is just for demonstration purposes. This will not work on a Windows 10 because, like I said before, the addresses will be different and all of that. I will explain also more about that later. But for now, let's just pick from our NTDLL. Okay, let's pick from here an address which is jump ESP and just use that. But this will not work if you reboot your computer, and I will go more about that later on. But for now, we just want to do this for demonstration purposes. Okay, so let's now modify this with our, so let's remove this, all of it, and let's modify that with 34. Why? Because this is little endian. 10, and then we have BC, and then we have X77. Yeah, I'm not going to do the same mistake again, so I forgot the X. Okay, so we have 34, 10, BC77. So this is where our jump ESP. And now let's replace this actually with NOPs. So we'll replace this with NOPs just so we can jump into that no operation. We have a breakpoint here, so that's good. Let's go back to the beginning. And now let's create our payload. So all good, everything is working correctly. Let's go and now load our bad file. Okay, so let's do this. And bad. Okay, so we can see the debugger paused. We're at the breakpoint. That's why it's saying paused. And you can see it's pointing to our jump ESP address because we overwrote. Where is it? Where is my fancy diagram? We overwrote this. Let me do. Yeah, we overwrote this actually with what? We overwrote it with this address. We overwrote this with this address. So here now we have 0x 0x. Okay, now we have this address. Okay, so we overwrote that, and that's why now it's at the jump ESP. If I hit F7 to like continue, we will be jumping where into wherever ESP is pointing. So if we go to ESP and if we like follow in dump, we can see this is where ESP is pointing to our knobs. So if we go back here, F7, we can see now we are in where in the knobs. So we can now slide all the way in the knobs, and then if we had our shellcode here, we can execute our shellcode. Great, let's modify our code, add our shellcode. Or what you can do sometimes just for, let's say, to make sure things are working correctly, I usually would like to add a software breakpoint here. Let me do that from directly from the code. And let's start here and let me update this. I'll call it number 4. So this is 4.py. Yep. And here what I will do is I will add, let's say, 4 of them. Okay. And I'm going to call this nope. Nops 1. Okay. I'm going to add 4 of them, or we have a lot of space, but 4 is enough. We can do that. And then I'm going to add my pad 1 equals, then I'm going to do the XCC, and I'm going to multiply this by also 4. And actually, let me call this breakpoint. Yep. And I'm going to add my pad 1, and I'm going to do the, I'm just going to send C's in there, or maybe more knobs. I'm going to just send C's for now, and then multiply this by, so we have 4 of these. We have 4 of these, the breakpoints. So we need to subtract from this one 8 bytes. So that means we have 76 left. Okay. And now if we run F5, we should create our payload, but oh, we missed 8. Oh yeah, because we didn't add it here. Good. So we have junk, then we have EIP, then we have NOPS 1, then we have breakpoint, and then we have pad 1. Yeah, that's why we missed those 8 bytes, 3000. See, my calculation is still working. Good. So let's go back here and let's try to load our payload. And before we do that, let's just add a breakpoint here, just to make sure we actually jump in there. But also the code we made now will actually create the breakpoint. So once we land on this, this is actually also a breakpoint. You'll see. So if I do now F7, so we're gonna jump. What did I do? Oh, I didn't load the file yet. Oh, okay, sorry. So we load the file. Bad bad. We're at the jump. If I hit F7, we are now at the knobs. Even if you hit F9, by the way, look what's going to happen. It's going to get stuck where? At the interrupt. Okay, so this is a breakpoint or an interrupt, which will interrupt the execution. So now we can control that or actually we know that our code jumped into the knobs and then slided into the interrupt. So we know we can control that. Now let's just update our code with some fancy shellcode. So, yep, remove that. And okay, and hit start. Now I'm gonna call this number 5. Okay, 5.py. And let's do some modifications again. So we have the knobs, we have the EIP, we have the knobs where we are gonna land. Then I'm gonna remove this. Okay, we don't need it anymore. What we can do is, let's see. We need our shellcode. So our shellcode should be here. So we can add, let's bring the shellcode. So let's get the shellcode here. I've already made those. And so let's use this, which is for the calculator for now. And then we'll add something else. So we can replace, I'm going to put the shellcode at the top just so I don't need, and I think this is 99 bytes. We'll check now. So let's do some updates to our code. Let's see, what do we have here? Sorry. And let's just, so we can see more. So we have the junk, we have EIP, then we want the no operations, then we want our shellcode, and then we want the pad. So this is 99 bytes. So if this is correct, then it means, where is my calculator? So it means 1976 minus 99. So we have 1877. 1877. Let's check. The good thing is our this one will show us how big our payload is. So let's just make sure we have everything right. So we have junk or the offset, we have EIP, we have our knobs, right? The 4 knobs. Then we have a shellcode, and then this is no longer used by us. I'm going to delete that, right? We have our knobs, then we have our, we can even just write here shellcode just for the sake of understanding and making things easier for you if you want that. So we can add this also at the end. So we have junk, EIP, no operations, then we have our shellcode, then we have our pad. Let's make sure this is 3000 bytes because I don't remember if this, okay, so it's not 3000 bytes. It means this shellcode is actually it's missing 4 bytes. So it's not really 99, it's 103. This is 103. I like to write that down usually just so I know how big my shellcode is. So we need to remove 4 more bytes from here. So this will be 1873. And now if we create our payload, we should have 3000 bytes. What did I do wrong this time? Oh, okay. Actually, we need to, so it's it should be 81, right? Or did yep, 81. So again, we have our 1012, which is the offset. We have 4 bytes, which is for the EIP. We have 4 bytes here, no operations, just to slide there. And then we have our shellcode, which is 103 bytes. And then we are filling the rest of the buffer with these C's, or actually I'm going to fill them with no operations also. So the rest of the buffer is going to be filled with also no operations. Let's run it again. 3000 bytes, great. Let's now go and execute our application. So if we open, but before I do that, I want to also add the breakpoint here. because I keep forgetting that. Yeah, good. So we have a breakpoint, and now we can go and load the bad file. Open. We are at the jump ESP. Okay, so if we hit F7, we are at the NOPs, right? Now we are at the NOPs. This is where our shellcode is. We are not gonna like step into one step at a time. We might do that later, but for now, I'm not gonna do that. If I just hit F5, then we should have, there's a problem here. Then probably we have some bad character in my shellcode. We probably have a bad character in my shellcode, but that's for another lab. For now, what I'm gonna do is, let me see if I run this from outside the debugger. We'll explain this in another video, but for now, let's just see if this is working. Okay. Oh, so we have something wrong going on. So maybe we have a bad shellcode. Let me see here. We have this all worked out correctly. I'm gonna add maybe 8 bytes for now. I'm gonna return this back to 77. Run and see. We will be testing this more or some similar example later to see where is the, because there might be a bad character in this one. I really don't remember, but it should be working. Okay, it did. So we needed to add more no operations. Probably when we jumped into those 4 bytes, and the since the shell code comes immediately after that, it doesn't work. And I will explain, by the way, why. Because this is because of the. Let me just go back here quickly. Let me just go back here. Get some coffee. And it's because of, let me start this. Okay, start. Okay. And let's get this okay, go back and now run the application. And if we open, again, I know what the problem is. It's because of the shell code is immediately after that. So let's go here just to show you. Jump ESP. So now, because these operations here, actually, they will overwrite some of the payload itself. And I'll explain what that is and how it works. These floating point operations, which are used to get PC. I will explain those, but this is the basics for now, and I don't want to make things complicated. So we'll get back to this. But now when we jump, we are not jumping into, let's say, anywhere here, and this is not going to overwrite these because there is still some space. And now if I hit F9, it should work. Our calculator is working exactly. Let's modify our code. So this is working great. Let's modify our code with a reverse shell, just so that we can have fun. UI, and I already have also created the reverse shell. So I'm just gonna replace that. So we have the reverse shell, and the length is 389. So we need to check that. So I'm gonna do, wait. Did I save this as another one, right? Yeah. So I'm gonna do this shellcode, and this one is, we said hash 389, and we need to update these numbers now. So So what do we need to do here? Let's go back to our calculations. I want to calculate this an easy way for you guys. So if we do 10, 12 plus 4 plus 8 plus 10, 12 plus 4 plus 8 plus 3, 8, 9, then we get this value. And if we subtract 3000, we'll get 1587. So we need 1587. Let's just double check. Yep. And let's save this. Now let's run this to make sure we have 3000 bytes. Oh, we are missing actually 21 bytes. So is this wrong then? 21 bytes. This makes this 1608. Is that right this time? Again, 1608, 3000. Great. So this is where our shellcode. So this is a reverse shell. Let's get our threat actor system. I already have everything set up here. So we can use this command, which is gonna create the load the console with the handler, set the payload, set my localhost IP, the port which the shellcode is to connect to, and the exit process, and then run. So if I just do that, to create my listener. Okay. Okay, so the listener is now running. As you can see, we set all the configurations. Now if we go back, I might do a video about Metasploit later, but yeah, for now we'll do this. So what do we need? Yeah, we need to exploit the application. So if we go VUPlayer, okay, and this time if we load the bat file, we should see something happen. And here we go. We can see that we have a reverse shell on the system. So we can do make directory hello, or actually just echo hello world into hello.txt. Okay, so just to double check, and we can see that file over here. Great, so we have access to the system, and we saw how we exploited that. Now, how did I generate the shellcode? Those were one of them was explained in the previous video. The Metasploit one, I will explain that in another video, but I think you already have, there's already a lot of videos out there and lot of resources, but I will also do that in a later video. How to generate that. Actually, maybe I can just show it to you now. Where is it? Yeah, here it is. So this is how I generated that payload. And it's 368. That's why when we did the calculations, we did it wrong. I thought it was 3. So how much did we say the payload here? Oh, this is 368. So this is 368. So that's why our calculations were wrong. So yeah, this is how you can generate this. MS Venom -P, the shell, the local host where it's going to be connecting to, the listener, the port where it's going to be listening on, and the exit function, and then the encoder which I'm using to encode the bad characters and remove them. -F, I want it's in C format, and -P to specify all the bad values, the bad characters, sorry. And again, we will explain more about this later. So all you need to do then, copy this into your shellcode. And as you saw here, where is it? This one, we can see we have access to that system. If I do ipconfig, you can see this is my IP address, my Windows. And if I check over here, you can see it's the same IP address. Good. So that's it for this video. I hope it was good or useful, and we'll see you in another video. Thank you and see you. Bye bye.